In this case, we're going to have a vector field that we're going to be integrating through a surface. So we're going to be integrating the flux of that vector field through a surface. Okay, so that takes a little bit of wrapping your brain around to really understand what we're doing. So I'm going to spend a little bit of time at the beginning giving you some real examples of when you would do this to give you a little bit of motivation. Okay, so let's say, for instance, you have some fluid flow. Okay, and the fluid's basically representative by a vector field because every little point in the fluid has a little arrow for its velocity and its direction. Okay, and so this thing may travel through a surface, some surface with some odd boundary, and you'd like to know how much fluid actually passes through the boundary in a certain time. That's basically going to be a flux integral because the fluid flowing through the boundary or crossing the boundary, the fluid is kind of like a vector field flowing through there, and the boundary is obviously the boundary, so you're actually integrating sort of that fluid going through that surface. Okay. Another example would be, how much of an electric field cuts through an area in a certain amount of time. Another example would be looking at the integral of an electric field, which is a vector field, cutting through a certain boundary, which could be an odd-shaped boundary, and you might be interested in looking at how the electric field and how much of it actually cuts through that boundary in a certain time period when you're looking at it there. Okay, so basically the flux integral is going to be written down like this, and I think if we just get started talking about it, it'll make some sense. It's going to be an integral over some surface, just like we had last time, denoted by sigma, except this time it's going to be a vector field dotted with something I'll tell you about in a minute, which is this unit vector here I'll talk to you about, and it's over ds. This is just telling you it's a surface integral. So it's an integral over an oriented surface n, okay? So this thing is just telling me I'm integrating over the surface given to me by sigma. Okay, that's all that's telling me. This thing is the vector field that I am integrating. Okay, and this thing is a unit vector normal to the surface. And what surface am I talking about? It's a unit vector normal to the surface here. Okay, a picture is worth 1,000 words, so I really need to just draw you a picture here, and I think you'll probably understand what's going on. So in three-dimensional space, here's your x, your y, and your z. Okay, let's say I have a surface that I'm going to actually integrate a vector field over, and this surface, let's say, is sort of a disk. Okay, and what I have here is I have some fluid that's flowing through, or some electric field that's cutting, or something like this, and that would look like maybe something like this. You'd have something like this. Could be a fluid flow that's going through here, so it has a magnitude and a direction. It could be a magnetic field going through here. It could be any sort of vector field that cuts through this guy right here. Well, in order to actually integrate it, I need to know how it cuts through, all right, but the way I'm going to actually pull that off is what I'm going to do is this surface, I'm going to define a unit vector that comes right out of this unit surface, and this surface, and I'm going to call it n. And so what I'm actually going to be doing is at every point on the disk, there's going to be a unit vector there, and I'm going to be dotting the field to this unit vector. And remember, the dot product really just tells you, basically, when you dot the unit vector, or I shouldn't call it the unit vector, the vector normal to the surface that I'm actually talking about. When I dot this with the field vector, what I'm getting is the component of the field that's going straight through. Okay, so when I dot them together, I'm really getting the component that's flowing through perpendicular to the surface, and then the summation over the surface actually adds them all up. So really what you're doing is you're adding up all of the flux lines. That's why it's called a flux integral. So if this were an electric field or a magnetic field, you'd actually be adding up how many flux lines, so to speak, are actually traveling through that surface. Now, I want to draw a situation that's a little more complicated to show you what you're doing kind of in the general case. It's really no different than what we've drawn here, but I do want to give you a little bit of exposure to a little bit more of a different case. Let's say that the surface is not such a clean, nice, and neat surface like a disk. You could be integrating over, let's say a pretty complicated looking surface like this. Okay, the surface could be kind of an egg-shaped surface, right? So if I were going to do that, then the unit vectors that would be coming out of here would be going at every single point. It would be going perpendicular to the surface. These are the unit vectors in everywhere, okay, all the way around. And even right here, it'd be coming out of the board towards you. Okay, so these vectors would be actually normal vectors. That's why it's called n. It's a normal, a vector normal to the surface. Okay, and so let me see if I can do my best drawing a real light picture here. But again, you could have, you know, the field kind of going through there, like this. Could be water flowing through the surface. Could be electric field or whatever. And so obviously, the field is going through. And at every point here at the surface, what you're doing is you're dotting the normal vector to the field vector, and so you're getting the component of the flow that's going straight through the surface. That's what that dotting is doing, okay? And then by adding up all of the contribution over the surface there, you're basically getting an honest-to-goodness count, so to speak, of these flux lines and how they're actually passing through the surface. You're looking at how they pass through compared to the normal direction straight out of the surface, and you're adding them all up. So you're adding up the flux going through, and that's why it's called a flux integral, okay? So let me just give you one quick example of kind of a rather famous oriented integral or flux integral that you'll study, or maybe you already have, and that would be the flux integral over some surface. You can pick whatever surface you want, of the electric field dotted with the unit vector normal to the surface, ds, and what you'll find in a book on electrostatics or something is that this is going to be equal to q over epsilon. Really doesn't matter, it's a constant. This is the charge, and this is just a conversion factor, okay? What this is really saying is, if you integrate the electric field dotted with the vector normal to the surface sigma, and you add it all up across the whole surface, and if it's a closed surface, if you integrate over a closed surface like this, you're going to get a value that's going to be basically telling you how many electric field lines or how much electric field permeates through the surface. That's what this is telling you. And what this equation is saying is that whatever you get here, that's going to equal the amount of charge inside of the surface. Okay? So what it's really saying here, I'm trying to give you a real life example, is if you have a collection of charges, protons or electrons or something inside of here, they're going to create an electric field, which is a vector field. So if you take a surface and kind of encapsulate that charge and do a flux integral, which is really just going to take the electric field, dotting it into the vector normal to the surface all the way around, that way you're getting an accurate count of how many field lines are actually cutting through the surface. When you actually do that integral, the answer is going to be equal to the amount of charge inside. So a lot of times in these kinds of problems, you'll be given an electric field, you'll be given some surface, and the question will say, how much charge is inside the surface? So you would do a flux integral over some closed boundary, and you would get a number. And the number would be how many or how much charge is really inside of the boundary. So this is one of Maxwell's equations, really, that's sort of derived for you here. That's one example of when you'd use this. There's lots of other reasons you would use a flux integral. I mean, they're used everywhere, but this is just one. Okay. So in order to continue and show you how to actually do the flux integrals, we need to talk a little bit more about the normal vector here. And what we're going to do is we're going to derive an expression that you're going to actually use in your problem. So what we need to do is talk about the vector n, okay? It turns out that there's two different orientations that n can take, okay? It's not hard to visualize it all, so I'm going to do that for you here. Let's say that your surface was kind of like a salad bowl, just for the sake of a drawing. That's your surface. That's the surface I'm going to integrate some flux over. And let's say that the normal vector pointed outside of the surface, so to speak. Okay? So this is outward. Okay, that points outward. Okay? And then let me show you what the alternative would be. You can also draw the exact same picture, x, y, and z, and you can also draw the exact same surface, okay, except this time the normal vectors, you could have them oriented coming inside the surface. Okay, notice in both cases the normal vector, the normal vector, which we're going to call n here, all of them, this one's exactly perpendicular to the surface at every point, and all of these vectors are perpendicular to the surface of every point. So no matter what surface you have, you could have a collection of normal vectors pointing outside, quote unquote, or pointing inside. And both of them are completely legitimate to use when you actually calculate the flux integral. It doesn't matter if you use the normal vector that points out or the normal vectors that point in. It doesn't matter. You can use either one. You're still going to get exactly the same answer, but there is a choice in how you do your problems normally, okay? So what I'm going to do is I'm going to present to you without proof the following, okay? If the surface sigma is written as f of x comma y, it's going to be a surface, okay? So that's going to be what your surface is. Then n is defined, and I'm not even going to prove it, as, so given the surface, okay, which is a function of x and y, this is not a vector field or anything, this is just an actual function of two variables that's going to describe this surface here, okay? What I'm going to do is I'm going to say if n is defined to be upward, which would be like this case right here, if n is sort of pointing upward, then what you're going to have here is this normal vector here, normal to the surface, is going to be defined, without proof by the way, negative f sub x, the partial derivative of the surface with respect to x in the I direction, minus partial derivative in the j direction plus k, okay, over the square root of f sub x squared plus f sub y squared plus 1, okay? I'm not going to prove it, that's just true. If you're given a surface, which is what we were doing in the last section and this section, then all you can do is take the partial derivatives, put it in here, and that's going to give you a normal vector at every point along the surface. Okay, it's always going to point perpendicular up, out of the surface. Okay, so then if you want to use the alternative, if n is down, which would be more like this one, okay, then the unit vector is defined. The normal vector is defined a little bit differently, and it's going to be defined as f sub x in the I direction plus f sub y in the j direction minus the k direction, all over the square root of f sub x squared plus f sub y squared plus 1. So you can see they look very similar. The denominators are the same. The only thing is that some signs are different in the numerator, and that kind of makes sense because, I mean, really, they're both vectors normal to the surface. It's just they're pointing in different directions. So there's basically a sign change in the top. So that basically one of these is the negative of the other. It's really not a big deal, okay? Now, when you're constructing your integral, when you're doing some flux integral and you have to decide what vector to use, it doesn't matter if you use this one or this one. You're going to get the same answer, okay? Not a big deal, but there is a choice there, okay? So what we're going to do next is we're going to continue building on this. We've talked about the normal vectors. And we know what the actual flux integral is going to look like. What we're going to do is use this and go and sort of derive a nice form that we can always use very easily to calculate the flux integral. Okay, so what we're going to do, don't forget, is we're calculating the flux integral over a surface of a vector field dotted with a normal vector normal to the surface, ds. Okay, and what we're going to do is this is a surface integral, really. I mean, what you're doing is you're dotting the things together and then you're doing a regular old surface integral. So we've done surface integrals in the last section and we're going to use a little bit of that knowledge here. You're just dotting two things together before you do the surface integral. So what I'm going to do is I'm going to write this as a double integral over the region R, okay, of the following. I'm going to write f as m in the I direction plus n in the j direction plus p in the k direction. That's just the vector field, really, is all it is. I'm going to dot this with the normal vector, okay, that I have, and that's going to be, I'm going to use one of these representations, negative, I'm going to use the upward representation, negative f sub x I minus f sub yj plus k. And in the bottom is going to be the square root of f sub x squared plus f sub y squared plus 1. All right. So what I've done here is this is just the vector field. The normal vector here is just what I wrote on the previous board. I'm just using that here. Now, what I'm doing is I'm dotting these things together and I'm integrating over the surface integral. From the last section, the section right before this one, when we're doing integrals over surfaces, what we did was we integrated the function that we had, and then we had to multiply that by a term at the very end there that we could then use to integrate the thing. And that term was this: f sub x squared plus f sub y squared plus 1. And then we did the whole integral over dA. So it's this dotted with this multiplied by this, okay? So what I'm trying to tell you here is, even though this is a different looking integral, it's still an integral over a surface. When you dot the stuff in the middle, you get something back that you then integrate over a surface. So we do the dot product here, and then after this point, it's a regular old integral over a surface, which we did in the last section. So in the last section, if you go back, you remember we integrated our function, then we always had to multiply by this stuff, and then we integrated over dA. So this is nothing more than that. You do the dot product, this term comes from the last section there. Now notice what we're doing. We multiply, these two things are dotted, then we multiply by this, but if you can kind of imagine this being over here, this denominator is going to cancel with this in the numerator, okay? And that's what's happening here. And so at the end of the day, what you're going to actually have is you're going to have, in order to do this surface integral, you're going to have this dotted with this. The denominator is going to exactly disappear, and that's going to make things a little bit simpler, okay? So what you're going to actually have at the end of the day when you look at this is you're going to have this double integral over the region R, and what you're going to be doing is you're going to dot this vector field into this stuff right here, okay? So let's go ahead and do that dot product right now. Let's dot each component into the components there. This guy is going to cancel, so he doesn't even matter. So what you're going to actually have is negative m, because negative 1 times m, okay? It's going to be a function of x and y, f of x comma y, okay? Let me write all this down and we'll get to the details of why we're doing it. Multiply by f sub x, which is what I have right here, which is the partial derivative, okay? Minus n x comma y comma f of x comma y, which is this guy, multiplied by dy, I'm sorry, by f of y. So the negative 1 comes, and that's why I have this, okay? Continuing on, plus p of x comma y comma f of x comma y. Okay, I'm going to get to explaining what this stuff is in a second. All right, and then this is just multiplied by 1, so there's nothing there. And so let me go ahead and close brackets on this, and I'm doing this entire integral over dA. Okay, this is really what you're gonna end up doing. This guy is going to be what you end up doing if the normal vector is oriented up. Okay, because that's what I used here in my normal vector here. Let me explain what I'm doing here. What we're doing is we're dotting each component into here. Okay, now if you go back to the previous section, when you were doing the surface integral, you take each component and then you have x and y, and then you plug in f of x and y in place of the z variable, and that's because we're doing this integral over the surface defined by sigma. So what we're doing there when we do that is we want to plug in the z value into here, because that actually bounds us in terms of the surface that we're actually integrating over. Okay, so this is actually pulling off the magic and telling us how we're actually integrating only over that surface. Z is equal to a function of x and y. We plug it into here, and then everywhere along the vector field that we're only evaluating on the boundary. Okay, this other stuff comes about because of the normal vector that we have to begin with. So we take our vector field, we dot it with this numerator right here because the denominators cancel. This is all this stuff going on here. The only thing is when we actually evaluate the thing, we're going to plug in x comma y comma f of x and y. We'll do some problems to show you this. This is what you will get if, this is what you use, I should say, if the normal vector is up. because that's what I used here. Okay. Now I'm going to write down without proof what you will use if the vector is oriented down. It's exactly the same thing. You'd put the down vector here, and it's going to look almost exactly the same because of these things only different by a sign. Okay. So if n is down, then what you use here to evaluate the flux integral is the following. Double integral over r of, basically it's going to be the negative of this. That's really the only difference between it. So you're going to have m x comma y comma f of x and y. And this is, when we plug this in, this is actually plugging the z value in as our surface is actually telling us only to evaluate the boundary of the surface. Okay, times f sub x, and then we're going to have over here plus n x comma y comma f of x comma y times the partial derivative with respect to y. Okay, and then we're going to have minus p x comma y comma f of x comma y, and that's really not multiplied by anything, and you're going to have dA. So you're doing integration over in the plane there, m, n, and p. And notice that these two things look almost exactly the same. This is the negative of this. You just multiply by -1 and you get this, and that's because the normal vector, if you're oriented up or down, just differs by a negative sign. Okay. So again, this is the form that we're actually going to use when we solve our problems, because what we're going to have is we're going to know the vector field that we're integrating over. So we're going to know m, n, and p. We're going to know the surface we're oriented, that we're actually integrating over. So we're going to know f of x and y. That's going to be our surface. So once we know our surface, we can calculate f sub x, f sub y, and then we'll be able to just plug it in here and integrate over the region R, which is the projection down in the xy plane. So let's go ahead and work and show how to actually do that. Okay, so the problem that we're going to do is going to be the integral over the surface sigma, which we'll talk about what that surface is in a minute, f dotted with a normal vector ds. So we're integrating over this surface, but we're integrating this vector field dotted with the normal vector going out. Okay, and so what I'm given here is that the force field that I'm actually dealing with, or the vector field that I'm actually dealing with, function of x, y, and z, is y in the I direction minus x in the j direction plus 8 in the k direction. That's the actual vector field that I'm integrating, and I'm going to integrate that as it flows through a surface, and that surface, sigma, is given in the problem is the part of the paraboloid, okay? The paraboloid z is equal to 9 minus x squared minus y squared above the xy plane, and also it's telling me that the vector n is directed up. Okay, so that tells me sort of what flavor to use for the relation that I'm going to use to solve this thing. So basically I'm integrating a vector field as it flows through a surface. It's a paraboloid, which just is a fancy word that means, you know what a parabola shape is, okay? It's a three-dimensional parabola, basically. So it's kind of like this, and it's sort of an egg shape right here, and it's sitting right on top of the xy plane, and I'm going to use that entire surface bounded by the xy plane coming up as a paraboloid. This flux field is flowing through it, and I'm really going to add up the contribution and see how much of it's actually flowing through there, okay? So again, when you're doing these kinds of problems, the first thing you need to do is draw a little picture of what it is you're doing. It'll really save your bacon a lot of times, okay? So it's a paraboloid, we talked about that, and that just basically means that it goes like this. That's a terrible paraboloid. Actually goes down like this. Okay, so you can imagine this is a parabola. It's sitting right on the xy plane, And by looking at this, if you just sort of look at this thing, z is equal to this function here. So at every point x and y, you're getting the value at the surface, okay? But if you put z is equal to 0 in here and find out what the thing actually looks like in the xy plane, put z is equal to 0 here, what you're going to get, put z is equal to 0, you're going to have 0 is equal to 9 minus x squared minus y squared. Let me move x squared and y squared over here. You'll have x squared plus y squared is equal to 9. This is a circle with radius 3. So what it's telling you is if you put z is equal to 0 in, which means you're looking in the xy plane, the shape is a circle, which makes sense. If it's a parabola, it's going to cut through the xy plane in the shape of a circle. That's going to be important later because when we do our integration in the xy plane, it's going to be a circle with radius 3, okay? That's basically what I wanted to show you there. So one thing that we found that we're going to need later on is the function f that defines the actual sigma that we're integrating over is equal to this 9 minus x squared minus y squared. Okay, it's a function of x and y. It's basically given to us in the problem. You're going to need later on the partial derivative with respect to x, so let's calculate it now. What you're going to get here is negative 2x. Okay, that's the partial derivative of this with respect to x. F sub y you're going to calculate as negative 2y. We're going to use that information later. So I think now we finally have all the information to actually construct the integral here, and let's go ahead and do that now. So the double integral over the region sigma of the field that I have dotted with the normal vector ds. You know, I could just take this guy here and dot it with the normal vector that I had given you in the very beginning of this class, and you'll get something out of it. But we derived the expression that you actually get when you do all of that. Okay, and what you're going to get is, what you're going to have when you use the unit vector oriented up is it's going to be the double integral over the region R, which is going to end up being a circle with radius 3 in the end of the day, and it's going to be negative m of x comma y comma z of f of x and y, this is just what we wrote on the previous board, times partial derivative with respect to x, okay, minus n of x comma y comma z, actually it's not z, I'm making the same goof every time, function of x and y, that's what you're plugging in here to tell you what path you're actually integrating the thing over, times f sub y, okay, plus p of x comma y comma f of x and y, okay. There's not multiplied by anything there if you look back, and that's what that'll be, and you're integrating this over dA, okay. So what are m, n, and p? Well, m is going to be given by this, n is given by this, and p is given by this. And I know what I've calculated for f sub x and f sub y, so I really know everything I need to know to set this integral up. So it's going to be the double integral over the region R. We'll worry about that later. Negative m. M is going to be the coefficient in front of I. So you're going to have y right there times partial derivative of f with respect to x. You're going to have negative 2x. Okay. Minus n, but n is given by negative x. So you're going to have plus x times partial derivative with respect to y of f. So you're going to have negative 2y, okay, plus p. P is given by 8. And you're doing it over dA. So what you're going to have is this right here. And you can simplify this just to go ahead and just combine some terms. You're going to have positive 2xy minus 2xy plus 8 over dA. Now look at this. This looks very nice because 2xy minus 2xy is going to give me 0. So moving on over here, this is going to be the double integral over the region R of the number 8 dA. That's what I actually have to integrate. Okay, that's really what I actually have to integrate. But notice that the region R that I'm integrating over in the xy plane is just a circle with radius 3. So of course I'm just going to go ahead and use the polar representation to do that because it's a circle. So the way I'm going to do that is I'm going to integrate of 8, and anytime you do polar you have to go r, dr, d theta. Okay, The limits of integration in r are going to be 0 to 3 because it's a circle with radius 3, and in theta it's going to be 0 to 2 pi because it's a full circle. So the first thing I'm going to do is I'm going to work with this. Integrating this, it's going to be 8 halves r squared, evaluated from 0 to 3. 8 divided by 2 is going to give me 4. And plugging this in, 3 squared is 9 minus 0 squared is 0. And 9 times 4 is 36. All right. And so I'm going to take that 36 and I'm going to integrate that from 0 to 2 pi 36 d theta, which again is a simple integral because it's a constant. So I'm going to have 36 theta evaluated from 0 to 2 pi. Okay? So I'm going to have 36 2 pi minus 0, evaluating the limits of integration. 2 times 36 is going to give me 72 pi, and that is the final answer. So let's go back over it and just make sure we understand it. We're doing an integral over an oriented surface. The actual vector field that we're integrating to find out how many flux lines actually go through this thing is given by this. It's a function of 3 variables, so it's a vector field that exists in all 3-dimensional space. Sigma is defined to be the part of the paraboloid given by this above the xy plane. N is directed up. Okay? So because this guy is the paraboloid, then the shape of the region in the xy plane that we're going to end up integrating over is just a circle. You can find that out by setting z is equal to 0, and you see it's a circle. The function f that defines the boundary sigma is just given by what's given to us in the problem. So we write that down and we take the partial derivatives because we know we're going to need those later on. Now the flux integral can be rewritten as an integral over that region R in the xy plane. We derived this in the previous page. You take the x component of the vector field, with a negative sign because I'm using the up notation for the normal vector. You take m, you put it in here, but multiply by partial of f with respect to x, n partial with respect to y, p, and you're integrating over dA. M I knew was y, and then n I put down here, and then p I put down here. The partial derivatives are given here. When I do the multiplication, these two things just subtract out and they go away, so it leads me to a very simple integral, integration of the number 8 over the region R, which was a circle, by the way, of radius 3, so I did it in polar. R dr d theta just comes from the fact that it's a polar integral, and you always have that. In dr, it goes from 0 to 3. D theta goes from 0 to 2 pi to give you the whole circle. And to integrate the inner integral, 8 over 2 r squared, which is 4 here, and then you just do the limits of integration, getting 36, and then integrate that over d theta, which we do here. Evaluating the limits of integration gives you 72 pi. So in this section, we've done flux integrals, which are basically integrals over a surface, but instead of just having a function there, you're actually integrating a vector field that sort of flows through that surface. So you can get into this in electrostatics when you have electric and magnetic fields that you want to see how many flux lines go through a certain surface. Fluid flow that goes over a boundary, you might be doing that. And basically, you have your vector field that's represented by these little lines or these little arrows, and they're cutting through a surface. So the way you do it is you dot the vector field into the normal vector normal to the surface, and you do the surface integral. Once you do that, the surface integral becomes the same as it is done in the last section. So what we've done is we've derived a procedure by taking the dot product there and integrating over that region sigma to basically arrive at this thing, which is sort of ready to sort of plug and chug. Once you know the vector field and the function, the surface you're integrating over, you just sort of plug everything in and do the integration in the xy plane, just like we did in the last section. Okay, with some practice, I think you'll get the hang of it. Just remember, you're looking at the vector field flowing through the surface, and so it really does have a strong analogy in terms of a water hose flowing through a surface or something like that. And that is how you do vector fields, integration of vector fields over oriented surfaces. That's also called flux integrals.
Learn anything at mathandscience.com.